Hello and welcome. In this video, I'll be covering section 3.3, which is over concavity and the second derivative test. My goal for you by the end of the video is to be able to determine the intervals in which a graph is concave up or concave down, to be able to find what are called points of inflection of graphs of functions, and to be able to use the second derivative test to be able to find the relative extrema of functions. So let's go ahead and start with talking about what concavity means. So essentially, if we were to think about a graph that's curving up, if we were to sketch all of the tangent lines as we're going, we would be able to recognize that the slope is constantly increasing along a curving up part of the graph. On that flip side, if we had a graph that was curving down, and again looked at all of the slopes, we would be able to see that the slope is continually decreasing over that entire place where the curvature is down. So this property is what we actually formally define as concavity, where if a graph is curving up or curving down, we can then say it's concave up or concave down. So if we look at the examples here down at the bottom, as you can see with the first one, we have essentially a parabola here, but if I were to sketch any tangent line, right? If I were to kind of sketch a few tangent lines along this graph, as you can see, on the far left it would be extremely negative slope. So the further left I am on this graph, the more negative the slope is. But from left to right, if I were to follow each of those slopes, I guess, or come up with each of those slopes, it would constantly be increasing and eventually become positive. So what we would do is actually call that a concave up. Let's try that again. Concave, if I could actually spell today. So concave up, basically on the entire interval from negative infinity to positive infinity for this one. If we look at the second example, as you can see, this has now got the curvature down. So if I were to again kind of sketch all of those tangent lines that are close to the graph, as I come up and around the vertex, now the slopes would start becoming more and more negative. So they're constantly decreasing as I go from left to right. So this one would be one that we would consider concave down. And it's technically always concave down because it's always curving down. So this would also be from negative infinity to positive infinity. Now the third example, you can kind of see that the origin really is where it kind of stops decreasing. So if we think in terms of each of these, its slopes are constantly decreasing. They start becoming negative, but once I get to that point at the origin, now those slopes start coming back and start increasing. So this one actually would have two different intervals of concavity. It would have one where it's concave down to start. So the concave down for this one looks like it would appear just graphically to be negative infinity until I get to 0. And then it switches to now starting to curve up after that. So it'd be concave up then from 0 until infinity, again because the curvature of that graph to the right of 0 is actually curving up the entire time. So even though the slopes started negative, they were constantly increasing, and it created that upward curvature, which we call concavity up. So hopefully those visuals at least give you an idea of what concavity really is. So now let's go ahead and talk about how we test for concavity. So essentially, if we think about what we're doing, we're looking to see when the slopes are increasing or the slopes are decreasing. And if we think about, well, slope is a first derivative, the rate at which our first derivative or our slope is changing should actually be the second derivative. So what we do for this is we actually need to find our second derivative. So notice with this, it does say that we're going to do f double prime of x, and we just want to figure out when is it greater than 0. So if we look at this one right here, when is f double prime greater than 0, then at that point we would say it's concave up. If we end up having our second derivative come back negative or less than 0, so this is now when f double prime of x is less than 0, then at that point we would say it's concave down. So as far as our guidelines for applying this concavity test, essentially what we need to do is just locate those values where the switches would happen. So that would be essentially when our second derivative is equal to 0 or it's equal to undefined. That's where it could potentially switch signs from positive to negative or vice versa. So it's very, very similar to the concept of finding critical numbers with our first derivative. We just don't happen to call these critical numbers because they're now associated with the second derivative. And what we do is we set up a sign line or set up some test intervals using those numbers. So that would be where a number line would probably be the best visual. And then we just pick numbers on each of those intervals, plug it in, and actually test. So we'll test what is the sign of each. Anything that comes back positive we'll be able to say is concave up. Anything that comes back negative we'll be able to say is concave down. And it is possible for you to go back to back, either both concave up or both concave down. If that's something that on a number line ends up happening, that's not a big deal. That more than likely means that it just kind of flattened out for a moment, but continued still curving up or still curving down. But we'll get into some examples, I guess, where that back-to-back positive signs or back-to-back negative signs happen. So when it comes to the number line, if you've made the assumptions that it will always alternate, it definitely is not always the case. You always want to make sure that you do choose numbers that actually fall on each test interval. So let's go ahead and try out an example here. So with this one, notice we have our function, and all the instructions are saying is determine where it's concave up or concave down. So with this, I'll need to figure out what my first derivative is. I'm going to go ahead and just rewrite this using a negative exponent since I don't want to have to use the quotient rule. So I could just rewrite this as that x squared plus 2 on the bottom is being raised to a negative 1 power. That should help with at least my first derivative. So if I go ahead and do that here, negative 1 would multiply with the negative or the 4 in front to make it negative 4. And then I'd have x squared plus 2 that's now raised to a negative 2 power. But that is a function inside of another function, so chain rule says I would need to multiply by the derivative of x squared plus 2, which would just be 2x. So if I were to simplify that, that looks like I would end up with having a negative 8x that would be multiplying with x squared plus 2 to the negative 2 power. Now normally I would move that negative power to the bottom. However, I'm needing to come up with my second derivative, and if I were to think in terms of what would be easier to deal with, I think this negative exponent and a product rule might be easier, but we also could drop it to the bottom and say that this really was negative 8x over x squared plus 2 quantity squared. So I could write it that way and think of it as a quotient rule, but I'm just going to keep it in the negative exponent, and I'll end up seeing that I have a product here, so I'll have to use product rules. So if I go ahead and go straight to the second derivative using the product rule version, I'm going to go with the derivative of the front, which would be the derivative of negative 8x, which is just negative 8, times the original second function. And in this case, it was the x squared plus 2 to the negative 2 power. Then I'm going to add that with, I'll keep the first this time, so that's going to be a negative 8x. That we'll need to multiply with the derivative of the second function, so this is going to be another chain rule, so negative 2 would come out front. X squared plus 2 will now have a power of negative 3 on it, and then multiply by the derivative of the inside, which once again is going to be 2x. So now if I simplify this, we can go ahead and say that the first one would be negative 8 times x squared plus 2 to the negative 2. Not much simplifying I could do there, other than maybe I could have moved that negative power to the bottom. But hopefully you'll see why I didn't do that here in the next step. I do have a negative 8x that's multiplying with a negative 2, so that will become a positive 16. And then I do have an x, actually, let's go ahead and multiply it with the 2x that's here at the very end as well. So I've got negative 8 times negative 2 times positive 2. That would actually give me 32. And then x times x would give me x squared. So I've dealt with all of the coefficients outside, and now I've got x squared plus 2 to a negative 3 power. So remember, when we're factoring ones like this, we want to take out whatever is more negative. It looks like I can take out an 8 as a coefficient. Yeah, I'll go ahead and keep it positive 8. I can't take any x's out, so that's going to stay, but I can take x squared plus 3 to a negative 3 power, and that would now leave a negative x squared plus 2 and a positive 4x squared from the second one. So it looks to me like I can simplify this a little bit. So I've got an 8 in the numerator. Looks like if I were to simplify this parenthesis right here, I'd have 4x squared and a negative x squared, which would be a positive 3x squared inside a parenthesis here, sorry. And then a negative 2 when I distribute that minus sign through. Then all over now, I can move that x squared plus 3 quantity cubed to the denominator to make it a positive power. So essentially, what do I need here? Well, I need to figure out when does this equal an undefined value or a value of 0. So if I were to set this equal to 0, I'd get 3x squared minus 2 equals 0. So add 2 over. I get 3x squared equals 2, divide by 3. So x squared equals 2/3, and then take a radical, which would give me x equals plus or minus square root of 2 over the square root of 3. I'd have to rationalize, so that would turn into square root of 2 times the square root of 3 in the numerator, which is square root of 6 over, and then 3. If I then also figure out when does the denominator equal 0, I could do x squared plus 3 equals 0, and realize relatively quick here when I subtract 3 and I get x squared equals negative 3 that there won't be any real solutions because the square root of a negative would give me imaginary. So at this point I wouldn't have to worry about undefined values because the denominator actually never is equal to 0. So now what we'll do is go ahead and set up a sign line. I got negative square root of 6 over 3 and a positive square root of 6 over 3. And I'm going to plug into, I'll try and use the different color here, I'm going to plug into this version right here on the left and just see what happens. So if I choose a number, let's see, negative square root of 6 over 3, probably a safe number would be like negative 10. Number between negative 6 or negative rad 6 over 3 and positive rad 6 over 3 would be 0, and then maybe positive 10 would be safe over here. So if I plug in a number like negative 10, squaring that, that'd become 100. Tripled would be 300. Take away 2, that's going to be positive. The bottom we've already established will always be positive because squaring a number and adding more to it will always be positive, and cubing a positive will stay positive. So it's really just the numerator that I need to worry about. And since 3 times 100 take away 2 was extremely positive, multiplying by 8 should keep it positive. So I've really got a positive over a positive. Just saying positive a whole bunch there. If I plug in 0, it looks like the numerator would be a negative 2 times an 8, which is negative. The bottom would be positive. A negative divided by a positive would come back negative. And a number like positive 10 should give me the same result as negative 10 because they're both being squared, so that should also come back positive just like negative 10 did. So now it turns into coming up with our final answer here. So our concavity, we can say it's concave up for the two intervals from negative infinity until negative rad 6 over 3. And starting at rad 6 over 3, going to positive infinity. And then in the middle there would be concave down on that interval from negative rad 6 over 3 to positive rad 6 over 3. And there's our concavity for this kind of uglier function. But we ended up getting what those values where the concavity would switch, identified and listed out in that interval format. So obviously that was a kind of ugly example as far as the numbers we were dealing with, but hopefully the concept of we just find the second derivative, find out where it equals either 0 or an undefined value, set up the sign line, and just test the intervals. Notice it's very, very similar to what you were doing with the increasing and decreasing. We're just using the second derivative instead of the first derivative, hence why it has a different concept, which we call concavity. So let's go ahead and talk about the next type of thing in this section, which is what's called a point of inflection. So essentially, a point of inflection is any time a graph has a point that's defined where the switch from concavity up to down happens, or even vice versa, concave down to up. So remember, with increasing and decreasing, when those switches happen, we actually call those extrema. Now with the second derivative, when the concavity is switching, we call those points of inflection. So what's nice about that is the point of inflection, essentially, if we know what it is, so if I gave you what the point of inflection was, say like 2, 3 or something like that, then we would know that the second derivative of that 2 or that x coordinate should either come back either 0 or potentially undefined for that particular thing. So it is kind of interesting that you can get an undefined value for the second derivative, but actually have the point b defined on the graph itself. That's not a big deal. As long as the point exists on the graph, we can potentially call it a point of inflection. Now, if it's not defined on the graph, in other words, you have a switch in concavity, but it's because it's an asymptote or something graphically, then at that point we wouldn't call that a point of inflection because it's technically not a point even on the graph itself. So let's go ahead and work through an example where we're going to go ahead and also do some more examples of identifying the concavity, but then actually analyze it a little bit further and determine whether we have any points of inflection. So this one might be a little easier because, as you can see here, it looks like it's going to be more of a power rule. But again, to start this process, to come up with the concept of concavity, I need to find a second derivative. So let's do our legwork to get that. So each one of these power rule here, so 4x cubed minus 3 times 2 would be 6x squared. 2 times 12 would be a negative 24x. And then the derivative of a constant at the end would be 0. Let's go ahead and find now this second derivative just by doing some more power rules. So I'd have 3 times 4, 12, x squared, 6 times 2, 12. This one has x, and then minus 24 for the constant. So this is what I'll want to set equal to 0. Since there are no undefined values, I don't have to worry about that. So the first thing I'm going to do is just try and make those numbers a little smaller and easier to deal with. So dividing both sides by 12, since 12 went into all three of those numbers, that would give me x squared minus x minus 2 equaling 0. That should be, I don't know why I put an equal over on the left there. That should be a relatively easy one to factor. Multiplies to negative 2, that adds to negative 1. That would just be a negative 2 and a positive 1. Which then gives us our two solutions of positive 2 and negative 1. So those will be the numbers that I put on my number line. And from least to greatest, negative 1 would come before positive 2, so I'll go ahead and set it up that way. We are going to plug into, I guess I could plug it into this factored form right here, since the 12 being positive out front, technically it was what this would be in factored form. So that 12 in front being positive is not really going to affect my signs. It's really just these two parentheses that I need to figure out what happens when I plug in some numbers. So number less than negative 1 would be like negative 5. Number between negative 1 and 2 would be probably 0. And then a number greater than 2, positive 5. Why not? So if I plug in negative 5 take away 2 would be negative. Negative 5 plus 1, that would be negative. 2 negatives, though, when I multiply, would come back positive. So that's going to be a concave up interval. When I plug in 0, I'd have 0 take away 2, which is negative. 0 plus 1, which is positive. A negative times a positive, though, would come back negative. And then a number like 5 take away 2 is positive. 5 plus 1 is positive. 2 positives when you multiply would stay positive. So now we can go ahead and discuss the concavity part. We know it's concave up from negative infinity until I get to negative 1. And then it's again concave up from 2 to infinity. We also can say it's concave down on the other interval, which in this case was from -1 to +2. But because of that idea, we can then say these two values right here are actually points of inflection. Because there was a switch in concavity, I can go ahead and say that there are points of inflection where those are the x-coordinates of it. So I know -1 comma some y value and +2 comma some y value are going to be those points of inflection. So I really just need to plug those numbers in to the original. Remember, to get y values, it's always plug into the original. So I'll need to figure out what f of -1 is, as well as what f of +2 is. So this first one would be -1 to the 4th, which is +1, minus 2 times -1 to the 3rd, so that should switch that to addition, so 1 plus 2. Then minus 12 times -1 squared, so that stays minus 12, and then plus 25. So if I were to simplify that, what do we got? -10, -9, and 25, -9, or 9 less than 25, that would come back equal to 16. Hopefully my mental math was good there. Let's just double check it here. 1 minus, or 1 plus 2, minus 12, plus 25. Good, my mental math was good. Next one's going to be a little bit tougher. 2 to the 4th, that would become 16. And I've got minus 2 times 2 to the 3rd, so that would be a 2 times 8, so that's going to be minus 16. That's kind of convenient. Then I've got minus 12 times 2 squared, so minus 12 times 4, which would be 48, and then plus 25 at the end. So that would be a -48 plus a 25, which would give me a -23. So that means that one point of inflection is at -1 comma 16. The other one is at 2 comma -23. And if we just think about the shape of this graph, or if you were to graph it on your graphing calculator or on Desmos, it probably is going to be something relatively steep. So the fact that those numbers are that far away from the x-axis probably isn't that surprising. But being able to come up with those values, again, we know that they're points of inflection because the concavity switched from up to down, then back to up. So 2 points of inflection would be just 2 extra points if I wanted to actually sketch a graph of this particular situation. It would give me a couple of extra points that I could plot that I know exist on the graph. And actually it would be where the curvature will change. So again, that's a couple of things that we can use when it comes to creating an accurate graph for kind of this uglier function, or that's more complex function than we've had to really deal with. Okay, so hopefully again, so far you've seen that there's very high connection between concavity, or what we do for concavity, as well as what we do for increasing and decreasing. It's just, again, we're utilizing the second derivative the entire time. Now, one thing we can do with the second derivative is we can actually do a test that will help us identify what some of the extrema are. So in other words, if we didn't want to take the time to actually come up with, is it increasing or decreasing, we could do what's called the second derivative test to determine whether I have a relative minimum or a relative maximum. I still would have to solve for, as you can see with this test, it says that I need to figure out when f prime of c is equal to 0, so I would have to figure out my critical numbers, and then I'll have to actually determine what is my second derivative. And then I essentially just plug the critical numbers from my first derivative into the second derivative and come up with what sign I actually get. So with this, notice the first example says if f double prime of that critical number is greater than 0, then that means it would, if we think about what that would mean according to just doing concavity, that would mean it's on a concave up interval. So the fact that that point would then be this low point of that concave up interval hopefully would not be too surprising. So it seems kind of counterintuitive that even though the second derivative is positive, we actually call that a minimum, but it's because it would be on a concave or a curving up part of the graph, which then means it must be the low point. And conversely, we can do the same thing if the f double prime of that critical number came back negative or less than 0. then at that point we could say that's actually a maximum, because that must be falling on a curved down part of the graph. And again, if it's the critical number, it's where the tangent must have been 0, or had a slope of 0, which means it must have been a high point or a low point. In this case, since it's on a concave down interval, we know it must be the high point or the relative maximum. Now, if you end up getting that the second derivative equals 0, then this test actually fails, so we would fall back to our first derivative test that we've already learned, where I would look for any switch in increasing to decreasing or vice versa to determine whether it's a relative minimum or relative maximum. So the second derivative test can be somewhat of a shortcut when you actually get a number that's not equal to 0, but when it does equal 0, then you have to kind of go back and try the other test to determine whether you have a max or a min. So let's go ahead and try out an example. Again, another one that's going to be a little bit easier than the first one we did, because again, this is just going to be a power rule situation. So let's go ahead and figure out our first derivative, which in this case, if I bring the 5 out front, that would become negative 15x to the 4th. And then 3 times 5 would give me another 15. And this one would be x squared. I do need my critical numbers, so I'll need to solve that one, set it equal to 0. So I'm going to go ahead and do that work here off to the side here. So negative 15 x squared, looks like I can factor that out. And that would turn into now a positive x squared minus 1. So notice I kind of did a little factoring as I was setting equal to 0, since they both did have a 15 and they both had an x squared. I went ahead, since the leading term was negative, took the negative out. So I can kind of see that my critical numbers here are going to be 0, and then x squared minus 1 equaling 0. That's going to give me a positive 1 as well as a negative 1 as my critical numbers. So again, these are the critical numbers that I'm going to plug into the second derivative, which I'll find here in just a second. And then if it comes back on a concave up interval, then I know it would be a minimum. If it comes back on a concave down interval, then I know it would be a maximum. So let's go ahead and figure out that second derivative, so I have something to actually plug into. Second derivative here looks like 4 times 15 would be, or negative 15 would be negative 60x cubed. And then 2 times 15 would be a positive 30x. Again, similar situation here. I may as well factor it. That's going to come back as a negative 30 that I can take out, along with an x. And then on the inside, that would leave a positive 2x squared, or yeah, x squared, then minus 1. And if I go ahead and just plug those numbers in, I know that f double prime of negative 1, if I were to plug that in, that should come back and make that front term negative. Or I guess maybe let's just set up a number line here. If I were to think in terms of where are these numbers, or what are the critical numbers of that, or not the critical numbers, the places where that equals 0. 0 would be one of them, and then I'd have to, if I set this equal to 0, I'd add 1, divide by 2, and then take the square root, so that would turn into a negative square root 2 over 2, a 0, and a positive square root 2 over 2 as my zeros of this. Again, if I were to do that, negative 30x equals 0, I get 0, just to kind of show where these numbers are coming from, since I did a lot of mental math there. Next one would be add 1, divide by 2, and then take the square root. Well, the square root of 1/2 is square root 2 over 2, as well as a negative square root 2 over 2 because of the plus or minus symbol I would get. But anyway, if I plug in negative 1 would be just a little bit left of that negative square root 2 over 2. So if I were to plug negative 1 in to that, I'd end up with positive 30 times, looks like 2 minus 1, which would be positive 1. So that's a positive answer. Or I could say that it just came back positive, don't really need the exact value. That just means since it's on a concave up interval, I could say that that must be a relative min at that number that has negative 1, comma, whatever the y coordinate is, which we'll find out later. For f double prime of 0, we can see that that actually will come back actually exactly equal to 0, because that was one of the critical numbers that I actually plugged in here, so that would have been right here. So since that was something that came back 0, I can't make any conclusion about that, so I may have to go back to my first derivative test, which we can do with our critical numbers in this area, and just figure out our increasing and decreasing to the left and to the right of 0, just to see if there is any switch. So I have no conclusion that I can make about 0 yet. And f double prime of positive 1 is one that we could plug in. That would give me negative 30 times 1, which is negative out front. 2 times 1 squared, take away 1, that would be positive. A negative times a positive would come back negative. So since that's on a concave down interval, that means it must be a high point for sure, which would be a positive 1 and then whatever its y-coordinate is. So I may as well go ahead and figure out what those two values are. F of negative 1 is going to be negative 3 times negative 1, so positive 3, plus 5 times negative 1, which would be a negative 5. So that came back negative 2. So negative 1 comma negative 2 is my relative minimum for this graph. F of positive 1 should give me negative 3 times 1 plus positive 5 times 1, which is positive 2. And then let's go ahead and double check the increasing and decreasing, see if we can come up with what 0 is, if it is anything at all. So if I were to figure out what 0 is, if I plug in a number like negative 0.5, looks like both of those, or negative 0.5 and positive 0.5, are going to be the two numbers that I would plug in. Squaring each of those, that should come back positive, so I'd end up with a negative 15. Let's see, what would that be? So negative 15 times a positive number, that's what, 1/2 to the 4th, so that would be 1/16. So negative 15/16 plus, and then 15 times 1/2 squared, so that would be 15/4. 15/4 is bigger than negative 15/16, so that would come back positive. And then a number like positive 0.5, that should actually do the exact same thing, because squaring it should be the same answer, so it was positive on both sides. So there is no conclusion about what 0 is. If we wanted to actually see if it's a point of inflection, we could go down to now our sign line for the concavity, plug a number like negative, let's see, rad 2 is a little bit more than 1, so negative 0.5 here again, and positive 0.5 are going to be the two numbers I could plug in, but now I'm plugging it into my second derivative now. 0.5 and negative 0.5, when you square it, would come back 1/4. 2 times 1/4 would be 1/2, take away 1, so both times the parenthesis right here would be negative. But the first time, the negative 30 times negative 0.5 would come back positive, so I'd have a positive times a negative, which would be negative. And then I'd have, with positive 1/2, I'd have a negative times a negative, which would actually come back positive. So I could, off to the side, say that even though 0 was not a relative min or relative max, I could say it's a point of inflection. And then the y-coordinate, pretty easy to figure out. Plug in 0 for both x's in the original function, and I just get 0 plus 0, which is also 0. So apparently the origin happens to be a point of inflection for this particular graph of the original function. And then I also was able to find my high point and low point of this particular graph, so it gives me a couple of extra things that I could plug in or plot, I guess, in order to be able to sketch a reasonable, I guess, rough sketch of what this graph would look like. And actually on the next slide I have what this graph looks like, so we can kind of see what happened here, get a little visual for it. So as you can see, it's kind of counting by a weird thing, but negative 1 actually is right there, and positive 1 is actually right here. So I got negative 1 and negative 2 was that minimum, positive 1 and positive 2 was my maximum. And then as you can see here at the origin, it did have a switch in concavity from being concave down to concave up, so that ended up having this idea of what we would call a point of inflection, since that was the newer concept that we talked about today. And we could have come up with, as you can see right here, this would be where that negative rad 2 over 2 came from, as well as right here, that's where the positive rad 2 over 2 would be coming from. So those actually would have been points of inflection, as you can see with the graphs, because it is concave down here, but concave up to the left of it, and vice versa on the other one. But we could have gone back and actually just go ahead and come back here. If we look at what's happening here, I'd only have to plug in one more number. I could plug in like positive 10. That would give me a positive inside the parenthesis, a negative out front. That would come back negative. So again, there are switches in concavity. So actually all three of these numbers were points of inflection. And again, if a question would have been asking for what the actual points of inflection are, I would actually want to plug in the negative rad 2 over 2 and the positive rad 2 over 2 to the original to come up with what the y coordinates are. But as we can see with this, we could come up with that y coordinate somehow, some way, just by plugging it in to actually get it. But it was only wanting what the extrema were. So anyway, hopefully that didn't just thoroughly confuse you guys. Again, concavity, key thing to remember is concavity is always something that deals with the second derivative. Increasing and decreasing is something that deals with the first derivative. And then all of your extrema are the critical numbers from your first derivative, but the second derivative test allows you to just plug it in to determine if it's on a concave up or a concave down interval, and then making a conclusion about whether that means it's a maximum or a minimum. So anyway, hopefully this will help with going through the homework. As always though, if you have questions, just reach out, let me know so I can try and clarify it. I do appreciate you taking the time to watch the video. Sorry for the length of it, but I guess we'll catch you next time.